Welcome to Chapter 2 of the Chemoinformatics Introduction series. In this lecture, we'll explore how to predict molecular properties directly from chemical structure. This is the core of QSAR and QSPR, turning molecules into numbers, then using machine learning to make predictions. By the end of this chapter, you'll understand molecular descriptors, fingerprints, and how to build your own property prediction models. QSAR stands for Quantitative Structure-Activity Relationship, while QSPR stands for Quantitative Structure-Property Relationship. Both follow the same principle. Molecular structure determines molecular properties. QSAR focuses on biological activities like drug potency, binding affinity, and toxicity. QSPR focuses on physical properties like solubility, melting point, and lipophilicity. The field has a rich history. Crum-Brown first proposed structure-activity relationships in 1868, Corwin-Hansch formalized QSAR in 1964, and today we use deep learning for state-of-the-art predictions. The core workflow is convert structure to numerical descriptors, then train a model to predict properties. 1D descriptors are the simplest molecular features, calculated from the molecular formula and basic structure. Let's look at aspirin as an example. Molecular weight is 180 grams per mole. Heavy atom count, meaning non-hydrogen atoms, is 13. Hydrogen bond donors, which are NH or OH groups, count as 1. Hydrogen bond acceptors, under the definition RD-kit uses, count as 3. Watch out here. Aspirin has 4 oxygens, so a naive count of every nitrogen and oxygen would say 4, and different toolkits really do report different acceptor counts. Always state which definition you used. Log-P, the octanol water partition coefficient, is 1.31 as computed by RD-kit, indicating moderate lipophilicity. Topological polar surface area, or TPSA, is about 64 square angstroms, and RD-kit counts 2 rotatable bonds. These simple descriptors are surprisingly powerful. Lipinski's famous rule of 5 uses just molecular weight, log-P, and hydrogen bond counts to predict drug likeness. RD-kit makes calculating these trivial with the descriptors module. 2D descriptors capture molecular topology without requiring 3D coordinates. They treat molecules as graphs and compute properties from that graph structure. The Wiener index is the sum of all shortest paths between atom pairs, measuring molecular compactness. The Balaban-J index measures graph connectivity and is remarkably consistent across similar molecules. Chi-connectivity indices capture branching patterns. More branching gives higher values. Kappa shape indices describe molecular shape in terms of linear versus spherical geometry. The beauty of 2D descriptors is they're fast to compute and don't require conformer generation. The Mordred library can calculate over 1,800 descriptors in one pass, more than 1,600 of which are two-dimensional, giving you a comprehensive numerical portrait of the molecule. Morgan fingerprints, also known as extended connectivity fingerprints or ECFP, are the most widely used molecular fingerprints in drug discovery. The algorithm is elegant. Start at each atom, then iteratively expand to include neighboring atoms. At radius 0, each atom is encoded by its own features. At radius 1, we include immediate neighbors. At radius 2, we include neighbors of neighbors, and so on. Each unique substructure found this way gets hashed to a bit position, creating a binary fingerprint. ECFP4 uses radius 2 and captures local chemical environments, while ECFP6 uses radius 3 for more context. The key insight is that similar molecules have similar fingerprints because they share substructures. This makes fingerprints perfect for similarity searching and machine learning. Not all fingerprints are created equal, and choosing the right one matters. MACCS keys use 166 predefined structural questions. Does the molecule have an aromatic ring, a carbonyl group, an amine? Each question becomes 1 bit. MACCS keys are highly interpretable because each bit has a clear chemical meaning. Morgan fingerprints, as we discussed, are learned from structure and can capture any substructure pattern. RD-kit fingerprints use linear paths through the molecule, which is computationally efficient. For similarity searching, Morgan fingerprints usually perform best. For model interpretability, MACCS keys shine. For large-scale screening, RD-kit fingerprints offer speed. There's no universal best choice. Select based on your specific task. Once we have molecular descriptors or fingerprints, we can apply machine learning. The pipeline starts with converting molecules to feature vectors, then splitting into training and test sets, training a model, and evaluating predictions. Ridge regression is a good starting point. It's fast, interpretable, and works well when relationships are approximately linear. Random forest handles nonlinear relationships better by combining many decision trees. LightGBM and XGBoost use gradient boosting for state-of-the-art performance on tabular data. For evaluation, we use R² to measure correlation, RMSE for prediction error magnitude, and MAE for average error. Always use cross-validation, typically 5-fold, to get reliable performance estimates. Never tune hyperparameters on your test set. Building accurate models is only half the battle. Understanding why they make certain predictions is equally important. SHAP, which stands for S-happily additive explanations, provides this interpretability. It comes from game theory and assigns each feature an importance value for each prediction. The SHAP summary plot shows which features matter most across all predictions. Features at the top are most important. The waterfall plot explains individual predictions. Positive SHAP values push the prediction higher, negative values push it lower. For molecules, we can even color atoms by their contribution to the prediction. This reveals which structural features drive activity or property values, providing chemical insight that can guide molecular design. Let's put everything together with a real example, predicting aqueous solubility using the ESOL dataset. This dataset contains 1,128 molecules with experimentally measured log S values, where S is solubility in moles per liter. We'll use 1,024 Morgan fingerprint bits combined with 10 RD-kit descriptors as features. Training a random forest with 5-fold cross-validation over the whole dataset gives an R² of 0.90 and an RMSE of 0.67 log units. The scatter plot shows predicted versus measured values clustered along the diagonal. Looking at 3 molecules from the dataset itself, glucose, with all those hydroxyl groups, has a measured log S of plus 0.74. Caffeine sits at minus 0.88, and anthracene, 3 fused benzene rings with nothing polar anywhere, is practically insoluble at minus 6.35. This simple model captures the key structural features affecting solubility. Let's recap what we've learned. QSAR and QSBR let us predict molecular properties from structure alone, enabling virtual screening of millions of compounds. Molecular descriptors come in different flavors: 1D descriptors like molecular weight and log P, 2D topological descriptors capturing molecular shape, and fingerprints like Morgan and MACCS encoding substructure patterns. Machine learning models ranging from ridge regression to gradient boosting can achieve excellent prediction accuracy. SHAP provides interpretability, revealing which structural features drive predictions. In Chapter 3, we'll explore chemical space and similarity searching, learning how to find similar molecules and visualize compound libraries. Try building your own solubility predictor using the ESOL dataset. See you in the next chapter.